Good morning, everyone. It's good to be here. Thank you to the organisers for the opportunity to speak with you today. I'm going to take us on a bit of an adventure, I guess, through some of the work that we're doing in nanotechnology, and particularly how we're trying to apply that in the areas of healthcare, and specifically in the areas of medical bionics. But I should put it in context, first of all. I'm not a healthcare expert. I'm a simple materials scientist with the occasional need for excursions into the healthcare system. And of course, the frequency and the duration of those seems to increase exponentially as the number of candles on the birthday cake increases as well. So I guess I'm becoming more of an expert in the healthcare system, not through choice, but through necessity. And I think I can hopefully show you today that even for us simple people who just consider healthcare to be diagnosis and treatment, you know, the old visit to the doctor and the look over the glasses that says something's not quite right, and that he has to recommend some sort of treatment. Hopefully that's pharmaceutical rather than surgical intervention, and we go off and we do it and hopefully return to normal, somewhere close to normal. Of course, things have changed as we've got older and as technologies advance, and the old-fashioned way of diagnosis is gradually being replaced by higher levels of technology. And there's a greater emphasis, I think, on continuous monitoring and preventative therapies, and so ways that we can maybe avoid getting to the stage where the cost of treatment is so high that it becomes sometimes even prohibitive. And it's technologies, of course, that have got us closer to that type of scenario, and I think we'll come back to that towards the end of the presentation. So material science has had a role to play in healthcare for a long time, but we just look at some very simple examples in the area of diagnostics. You know that glucose sensing, personalised glucose sensing, is now very commonplace. And of course that was made possible by advances in material science that make that little transducer very selective to glucose in blood. You can imagine that's a very complex chemical environment. And yet through advances in material science we were able to extract information that's critical to people who need to know that level of glucose in the blood for ongoing treatment. In the area of drug delivery systems, advances in polymers on a daily basis, polymer formulations that carry drugs to particular parts of our body, enhance the effectiveness of those drugs, and also maximises the efficiency of those pharmaceutical treatments. So polymer formulations are quite critical in healthcare as well. In the area of implants, perhaps the material science is more obvious, because obviously the material that a stent is made of, for example, we're trying to get an unblock an artery, is very critical. And so that material and advances in those materials, both in terms of their structural integrity, but also their functionality, is very important. So at the moment, for example, you will get a stent that's implanted and is there for life. A lot of the companies involved in stents, and we're involved in one of these projects, is looking at how we can create a biodegradable stent. So a stent that will unblock the artery and then disappear, and therefore not interfere with further biological function. So critically dependent on advances in material science. Perhaps the highest level of sophistication in terms of how we use material science in medical devices is in bionics. So bionics, I think most of you will have encountered bionic devices at some point in time. Bionics is where we're looking at interfacing the worlds of biology and electronics, so therefore the term bionics. Probably introduced by Luigi Galvani in his famous frog's legs experiments. You might remember where Luigi Galvani got the electrodes into the frog's leg, you twiddle the leg and you get an electrical impulse, and the reverse is also true. But most of us were probably introduced to bionics by television, by the $6 Million Man or the Bionic Woman. And it's interesting that at the same time we were learning about bionics through television, there were scientific researchers who were taking this area very seriously. And one of those was Professor Graham Clark at the University of Melbourne, who, in parallel with these developments, was looking at creating a real bionic ear, a bionic ear that would help profoundly deaf people to hear. And Graham and his team were successful. They developed the advanced cochlear implant electrode, shown here. And that electrode consists of 22 different platinum electrodes, very small electrodes, each individually addressable, It's implanted into the cochlea of profoundly deaf people. There's a microphone on the outside of the head which picks up the sound. It codes that sound, sends it down the wires, and stimulates the nerve cells that normally would not be stimulated. And so a profoundly deaf person can learn to hear or hear again. So an amazing invention. Professor Clark heads up the Medical Bionics program in our ARC Centre of Excellence. And even still, when this particular device was invented, it used platinum microelectrodes. There is a quest to develop other materials that will more effectively interface with nerve cells and therefore improve the fidelity of something like the cochlear implant electrode. Similarly, if we can interface with nerve cells more effectively, then there's the potential to direct nerve cell growth, to reconnect nerve cells, and therefore look at treating injuries such as peripheral nerve repair or maybe even spinal cord regeneration. So materials in medical devices are quite critical, from some very fundamental levels, some very rudimentary materials, right through to very sophisticated materials. It's not surprising then that nanotechnology has had, or is poised to have, quite a dramatic effect on medical devices, because nanotechnology has in the last 20 or 30 years revolutionised materials science. Now it is true that nanotechnology is not a new area. We've stumbled in and out of nanotechnology discoveries for centuries. Never probably called it nanotechnology. But it's also true that in the last 20 or 30 years, it's the first systematic excursion into this area in order to try and design and develop materials based on control of the nano dimension. So what do we mean by nanotechnology? Well, if we look at the size of matter, the size of materials, we just start down at the molecular level, which we're all familiar with, I think. And we're probably familiar with the micron level as well, because we're talking about silicon transistors. Put it all in perspective for those. If we have a look at the diameter of a human hair, it's about 50 micron. If we divide that by 1,000, we'd have 50 nanometers. So we're down at 1,000 times less than the diameter of a human hair. And we're in this world here between the molecular level and the micro-dimensional level. In physical materials, the physical material sphere, that's silicon transistors. On the biological sphere, we're talking about a nerve cell, for example, is about 20 micron. So we're talking about right down below the level of some biological systems. But the initial interaction of most biological systems will occur on the nano domain. So that's the type of area that we're interested in, how we can explore this nano domain and introduce some unique properties into materials. Now we have a particular interest in electro materials, as you've probably seen on the slides. It's the ARC Centre of Excellence for Electro Materials Science, but that's just a subset of materials, and these are materials that conduct charge. They transport charge or they transfer charge. And we're interested in how we, within the centre, how we might be able to design and develop better electro materials, and how we might characterise those, and then how we might use them in areas of energy and medical bionics. And I'll talk today about medical bionics. So electromaterials, just to give us a bit of background on electromaterials, just about everything we do today will depend on electromaterials, the ability to transport or transfer charge. And of course those electromaterials, as has already been alluded to, also need electricity and energy. And so we are very dependent on electromaterials. The simplest example is probably the common battery. How much can we do today without batteries? Not much. The common battery, two electromaterials, two electrodes and an electrolyte, transfer of electrons from one electrode to the other to generate charge. Even with these simple electromaterials, as we delve down through the micro domain, the diameter of living cells, as I explained before, right down to the nano domain, even for a given simple composition, we can induce some extraordinary properties. That's the exciting thing for a material science. That's the exciting thing about nanotechnology. The ability to change properties simply by changing size. For a given composition, changing properties by changing size. So we can change physical properties. They will conduct charge faster. They'll transfer charge faster. And we also change biological properties. Changing the nano domain, we can, for example, tune a surface so as it interacts with a particular type of living cell, or it repels a particular type of living cell. So it's the combination of these advances in the physical world and the biological world through nanotechnology that we want to utilise to create new platforms for medical bionic devices. Here's our only chemistry slide, I think. You don't have to memorise this formula, but I just needed to remind me about the materials I'm going to use for an example today. These are interesting materials. They're polymers, so they're plastic materials like everything else that's sort of around us today. Lightweight, low density. Interesting thing is they conduct electricity. These are one of the types of materials we're exploring in the centre. So polymers, plastics that conduct electricity. Polymers, of course, are normally very highly insulating, but you can adjust the structure so as we conduct electricity. The interesting thing about these, if we're talking about bionics, is they're organic in nature. So unlike our metals, which of course are metallic in nature, and we're trying to interface these hard metals to biology, there will be some limitations. Here we have a material which is a conductor. It can transport or transfer charge, but it's organic, totally organic in nature. So inherently much more compatible with biological systems. And here's just to remind you what we're trying to do is to bridge this interface, biology and electronics, using these types of materials and using nanotechnology to adjust the properties of those materials. I said there was only one slide with chemistry. I apologise. There's two. Don't worry about these. What I'm going to show you, the pictures behind these experimental results are more important. So these materials, that polymer I just showed you, can be electrically stimulated. It can transfer charge and it can take that charge into a biological system, or it can monitor a biological system by generating charge. You can electrically stimulate these polymers to induce all sorts of changes in the polymer material. And that's important when we're trying to create a bionic interface. So if I take that polymer and I put drops of liquid on it, for example, I can put in small amounts of charge and repel that liquid or attract that liquid. Very important in designing a biological interface where cells are predominantly made of water, biological systems. So this is usually the first consideration. How can I control the surface energy of a platform that I want to do biological interactions on? Well, these polymers, we can do it simply by small amounts of electrical stimulation. We can also take that polymer and load it up with drugs or growth factors. Protein growth factors might stimulate nerve cell growth, for example. And again, we can stimulate that polymer. And imagine if nerve cells were growing along here. Here's the drug. I've got a coloured molecule being released here. But the drug being released in response to the electrical stimulation, exactly where it's needed and when it's needed. So a very powerful tool in designing a more effective bionic interface. We can even design the polymer structure so that we can induce movement in the polymer with injection of charge, which is compatible with biological systems. That's important. All of these changes, I'm putting charge in that's compatible with the biological system. Only a couple of 100 millivolts. And you can see you can induce quite dramatic movement in the structure. They're a couple of centimetres long. You can get it right down to micron dimensions. And it's all quite reversible. And we know that biological systems will respond to movement or respond to force generation. Muscle cells, for example. So here's what we want to do. We want to use those materials to bridge this interface, and we're just going to look at the cellular level, and if we've got time, the skeletal level right at the end, because it's another interesting story. So here's our platform again. This is our conducting polymer, that polymer that conducts electricity. This is a Cochlear explant from a guinea pig. You can see the nerve cells thriving quite successfully on that surface. And a measure of how well they interact with the surface is how many neurites come out of that explant, how many of these neurites, and the length of those neurites. We found that we can design the polymer surface so that the number of neurites is high, depending on the protein we incorporate or into the conducting polymer. And also we can get a double benefit through direct electrical stimulation of the nerve cells. So we've got a surface where we can stimulate interaction with the nerves. An important finding in trying to design, for example, a more enhanced performance cochlear implant electrode. But you'll notice those neurites are growing in all directions. There's no control over the direction of growth. And so recently we've looked at, still using our conducting polymer platform. Here's our explant again. Now it's got got tracks. These are micron dimensional fibers, biopolymers, which will actually provide a topographical cue to direct the growth of the neurites. So imagine then if we were trying to reconnect nerve systems, then we do need control over direction of growth. The dimensions of those fibers are micron dimension. It was somewhere we had to start because we had to figure out how to make nano-dimensional fibers, which of course would be more efficient because these occupy far too much volume to enter a real conduit. So we've developed some techniques along with others. It's a technique called electro spinning, which enables us to make nano-dimensional fibers. So now it's 1,000 times less than that other fiber we looked at previously. We align these nano-dimensional fibers, and again, we can find that we can direct the cell growth. Here you can see the cells growing along this nano-dimensional scaffold in a particular direction. So these recent findings then have established for us a very interesting platform for either an enhanced performance bionic ear or for peripheral or perhaps even in the future spinal cord regeneration. I skipped over a couple of slides there which have to do more with characterizing. Let me just go back and show one. Another interesting advance as well as a challenge in the nanotechnology area is the ability to actually study and see what is going on in real time. And so not only do we have to develop new ways to make the materials, we have to develop new tools to look at them. And this is one of those tools. It's a technique called atomic force microscopy. Without going into the details, let me show you what it does. Here's our nanofiber. Here's the neurite. You can see they're very similar dimensions. And you can actually see little filopodia coming off the neurites. But these images are gathered in you can do this in real time in a biological environment. This is not an electron microscope where you have to work in vacuum. These are characterization tools that enable us to look at living systems in real time and the effect of materials developments and the effect of electrical stimulation on those systems. So advances in those tools which enable us to view the nano world are also very exciting. But to the other extreme, nanotechnology is often looked at, and you look at those images, and if you're a materials scientist, you get incredibly excited. But there's some really simple, pragmatic advances that arise from nanotechnology as well. The materials I've introduced to you today, these conducting polymers, for example, are very difficult to process with traditional technologies, traditional fabrication technologies. As we make nano dispersions or nanoparticles of those materials, we can actually subject them then to a lot of very simple processing and fabrication methods to make devices. So before we could make the nano dispersion, it was very difficult to turn these into devices. Our nano dispersion now really just becomes like an ink. And pigment inks have been used for a long time. So as I say, we have had these, we have delved into nanotechnology over the centuries, and now we're doing it in a systematic way. Here we have this ink which contains these very small particles, and what that means is we can start to create devices based on these materials, either by inkjet printing or other types of printing technologies. We can just print down the device. We could print in 3 dimensions. We've built a 3-dimensional printer so that we can print out our biological device or our nerve repair conduit. So you start to open up possibilities in fabrication. Similarly, we could spin just using textile spinning technologies. We can spin these long lengths of the fibers that we might need at the micron dimension, or as I've shown you already, electro spin nano-dimensional fibers. Because we can move into these controllable nano dispersions, it opens up many fabrication options. A simple fabrication option is to make an ink which is fairly viscous and then just use screen printing. Most of us would probably use screen printing at some point or another to screen print t-shirts and things. So a simple printing technology, but a very sophisticated device at the end. We've used screen printing to coat conventional textiles or fabrics with our conducting polymer and to build what turns out to be wearable sensing technologies based on traditional textiles. If we coat, for example, lycra with the conducting polymer, we find that as you it does take on electronic properties, so now it's an electrical conductor. And if you stretch the lycra, I do have some, but it's in my briefcase. If you stretch the lycra, you can change the conductivity of it. And we had a little demonstration we used to show people on lab tours. It's called the groaner. You probably can't hear that, but let me see. You can hear that. But as you stretch it, you can generate a sound from the textile system. And we had that as a simple lab demonstration. And one of our colleagues, Professor Julie Steele, visited the lab, and she works on biomechanics. And Julie immediately recognised an opportunity to take this electronic textile and turn it into a wearable sensing technology. Julie had worked for many years with the Australian Football League in trying to train footballers how to land properly so that they didn't damage their knees. For our visitors, if you haven't seen Australian rules football, I recommend that you try and have a look at it. It's a very interesting sport. It's very physical. People jump in the air a lot to catch the ball like this, and then they have to land, and they have to land appropriately to avoid damage to the knees. So Julie had worked with the Australian Football League for many years, developing training routines. But there was no feedback to the footballer as to whether they'd actually landed properly or not. They would have to do three-dimensional video recordings, then go back and try and get that information implanted into the footballer's brain after the session had finished. Not a very effective way to deal with footballers. I must say that this also has proven difficult for some footballers in terms of adapting the technology. But that's the challenge we live with. So we developed a very simple sleeve which used these wearable electronic textiles. And when the footballer then landed with the knee at the appropriate angle, they were notified immediately by a simple sound coming from the knee sleeve, which turned out to be a very effective training tool. And now we're looking at these wearable sensors for rehabilitation as well, in monitoring joint movement. So you probably can't hear that, but as the footballer lands at a particular angle, he gets the reinforcing sound that he's going through the exercise routines properly. We've taken that technology with many of our collaborators, and most of this with Professor Julie Steele. Julie's also had an interest in sports bras and how they can be designed in order to function better, and so we've incorporated sensing technologies into that. We've incorporated sensing technologies into shoes with some of our collaborators at Dublin City University, and started to take these wearable sensing technologies to a new level in terms of wearable chemical sensors or biosensors as well. So now instead of just monitoring movement with these types of materials, we can adjust the chemistry so that we can, for example, automatically sample sweat and look at some biological indicators in the sweat. So this is all a lot of information, and we're going back to that very first slide, or second slide that we had. It says that we are developing technologies that make ongoing monitoring much more simple and much more readily achievable. Of course, it generates a lot of information. And so it's not only advances in materials science that are important if we're going to implement this technology, it's also advances in information technology. And of course, the network is already there. In order to transmit that information to where it's required, whether that's your physiotherapist or your medical practitioner, the system is there to transmit the information once we've refined the materials and the interface, because it's the materials that provide the interface, whether it's at the implantable level, where it's got to interface with cells, or whether it's at the wearable level, where it has to interface with the skeletal system. The materials provide that interface and how effective that interface might be. So as I say, it's not just advances in material science, but advances in information and communications technology being used in healthcare and benefiting from these rapid advances in nanotechnology and how that's used in improving and controlling the properties of the materials that we use. So we started with the question, will it revolutionise healthcare? And again, I had the proviso or the rider that I'm not a healthcare expert, but I use the healthcare system on a more regular basis than I'd like to. I think there's no doubt that if you look around in laboratories around the world, what's happening in interfacing the world of biology and electronics using new materials, there's some incredibly exciting advances occurring. And whether that's at the cellular level or whether it's at the skeletal level. And that's not just for monitoring, but it's also for controlling the human system. And so I don't think there's any doubt that it will revolutionise the technology used in healthcare. How readily that will be implemented in the healthcare system, of course, is another and maybe a much more important question. Someone asked me a question the other day, can you teach a dinosaur how to do Irish dancing? And maybe this will be similar to trying to get some of these technologies into the healthcare system. So the technology will be there. The question will be how readily can it be adapted by what is understandably a very conservative system. And no one likes revolution. I don't think any of us are particularly keen on revolution. Unless, of course, we find ourselves in the midst of a crisis. And maybe there is a crisis just around the corner that will force us to implement some of these technologies in a more rapid and a more effective fashion. And I think that crisis is the ageing crisis. If we look at and this is well known around the world, and you'll hear it debated in many different, with different types of audiences, but there's no doubt that the population is ageing. And we have to age in a more effective manner. We have to interface with new technologies if we are to encourage active ageing. We need more monitoring systems. We need systems that will help us to continue to be active, preferably in our own homes. And the ageing crisis might just force us to look very carefully at what we're doing in healthcare and to realise that we do need to implement these exciting new technologies a little bit quicker than what we're doing at the moment. That last bit at the bottom probably needs updating. I think that was before the Greek crisis. I don't know if the over 65s are still worth $3 trillion. Acknowledgements. So I'm going to leave you with that thought. I think that there's lots of exciting technologies. How they get introduced into the healthcare system will be a real challenge for all of us. We work very closely with clinicians around the country and overseas in trying to develop practical applications of the materials that we're working on. We're very keen, as is Professor Graham Clark, to see these implemented in real clinical solutions, and I think the challenges are before us in the next 5 to 10 years to do that. And you can imagine to achieve or to work in this area requires a very multidisciplinary team. We do also within the centre have a very strong ethics, research and training program for our PhD students and research fellows, and you can imagine with some of these areas we work in that's a very important element of our research activities as well. We work down on the Innovation Campus. We refer to this as the old campus. So if you'd like to see the new campus, please come and visit us at the Innovation Campus. It's just only probably 5 minutes drive away. If anyone's interested in coming to visit or have a look around our laboratories, we'd be only too happy to organise a tour or to have a walk around for you. So again, thank you to the organisers. I didn't say it at the start, Judy said it, and welcomed all of our international guests. I'd just like to echo those sentiments. Wollongong is a tremendous place to work and a tremendous place to live. So I hope you have an opportunity to experience the living as well as the working over the next few days. And I'm sure from looking at the program, it's going to be a very exciting few days for all of us. So my last thank you is to the international research community. We have lots of collaborations, and as you can imagine, working in an area like this, I've said it's very multidisciplinary. It also requires a lot of expertise and a lot of resources. There's no way known that we here in Wollongong, there is no light for Wollongong, that's why I'm using the laser. We here in Wollongong cannot achieve or tackle those big challenges by ourselves. And so it's great to work in a scientific and a medical research community where these challenges are seen as global challenges and that we can play just a very small part in trying to overcome some of the things in front of us. Thank you very much for your attention this morning.
Sure. Are there any questions for Gordon very quickly? Yes.
You talked mostly about monitoring human systems, but then you also mentioned controlling human systems using these polymers.
Yep.
Could you talk about some of the applications? And since this is societal applications, I'm thinking, like, are law enforcement people thinking of controlling prisoners using this, or?
Well, they have the appropriate suit, I'm sure it could be arranged. So that control, of course, can be at all sorts of levels, the cellular level or the skeletal level. So in terms of the cellular level, we're looking at nerve cell control and how they grow. At the wearable level, though, remember I did show that you could make these polymers move. And so you do have the basis of an artificial muscle technology. So for example, we're developing a rehabilitation glove with North Shore Hospital, which has wearable muscle fibres, which enables someone who has very limited or no hand movement to be able to grasp things, for example. So it is possible to have skeletal control as well using wearable artificial muscle technology, and that's being developed. I haven't thought of all of the implications for its application, but I'm sure there'd be some interesting discussion on that.
Any other questions?
Just one quick question. On the polymer, electro material, the transverse charge, is there a way to create a non-conductive housing, perhaps, to protect that charge on its way? Or?
Yes, yeah, definitely. So, you know, there are lots. Most biopolymers are actually electronically insulating, and so the simplest way to do that would be to encase, much like you would an electrically conducting wire in the building, encase it in an insulator, and that insulator would actually be a biopolymer, something that interacts quite well with cellular environments, for example. So you can make coaxial biofibers which would have those properties you described. There's one up the back. I should let the chairman do his job.
Gordon, you talked to us about prosthetic devices somewhat. Can you see people opting into enhancements with the type of technology you're presenting as a benefit to them and their social living standards?
Yeah, it's a question that we sort of discuss quite a bit, and you can imagine Sue Dodds, who heads up our ethics research program, it's one of her favourite questions as well. There's no doubt that as the technology advances, that there's the possibility of delivering beyond human performance. So now how that will be applied and where it will be applied will be interesting to see. But I think we'd be naive to think that we won't develop systems. We might not, but systems won't be developed that will go beyond existing human performance.
One last question.
I understand there's about 400 odd products on the market at the moment that use nanotechnologies. Labelling legislation in Australia doesn't require that they be identified as such. Do you have a view on the labelling of these products?
Yeah, look, I think nanotechnology is no different from any other type of chemistry. I mean, all of the safety and toxicity things should be done, and I think people, should be aware of what they're using. Absolutely. I don't see why they shouldn't be labelled, to turn that question around. And there should be no fear about that labelling either, because if the toxicity tests are done, and they should be, before they go into the products, then there should be no issue with that.
Well, I'm sure we could ask Gordon a lot more questions, but we've got to stop at this stage. Thank you very much for